Welcome back. In this lesson, we'll talk about network assembly. I'll talk about why we need a network assembly language and what a network assembly language can do. I'll then talk about a specific example of a network assembly language called NetASM. I'll give an overview of the language, a brief discussion of assembly language primitives, and I'll also talk about various open issues. OpenFlow's design was motivated by the underlying device layout of the hardware, so the controller and the control protocol is limited in supporting new functions that are not supported by OpenFlow. New chipsets that we've looked at, such as RMT and FlexPipe, are adding new data plane functions, and new languages are specifying data plane functions at a much higher level. We looked at an example of such a language called P4. The question, of course, is what lies in between a high-level specification language like P4 and the programmable chipsets like RMT and FlexPipe. In essence, we need a network assembly language, which is a low-level programming language for programming network devices that provides a one-to-one correspondence with the underlying hardware and uses well-defined constructs to define low-level packet operations. The idea behind a network assembly language is that because it provides this one-to-one mapping with the functions provided in the underlying hardware, the assembler can enable writing highly optimized network programs, and it can make it easier for a compiler to generate an optimal layout. A common hardware architecture might look like this, where we have input interfaces leading into packet parsers, followed by a packet processing pipeline, and then queues on output. We've been talking about using OpenFlow or some other API to manage the state in a switch, but what if we wanted to specify the packet processing and parsing and make it more flexible? This is what a network assembly language enables. In our network assembly language, we'll be able to explicitly specify how to parse packets and process them before sending them to output queues. Programming in network assembly entails explicitly describing the processing pipeline in the assembly program, specified as a series of instructions or a sequence of operations that form an acyclic directed graph. A parse graph also gives semantic meaning to the bit locations in the packet header. This parse graph is specified by the user at the time of writing the assembly program. NetASM has three types of instructions: initialization, which creates state elements such as tables and registers; topology instructions that define how a packet traverses and is processed in the data plane; and control instructions that allow external controllers to populate states using control protocols such as OpenFlow or other open interfaces. Programming a hardware pipeline also provides the opportunity to implement what are called locally contained applications, where the hardware can update its states, such as registers and tables, locally without sending packets back to the controller. These locally contained applications mandate a new construct called update that updates the internal states, such as registers or tables. It has somewhat the opposite semantics to that of a modify construct, which updates packet header or metadata. In this case, a packet that triggers an update construct actually updates the local state on the switch. An example where locally contained applications come in handy is a Mac learner. Because we know exactly how to update the state at a switch when a packet arrives, there's no need to shunt a packet to the controller. The switch can instead update all of its state locally according to a predefined specification. One of the goals of NetASM is protocol independence, or the ability to compile from different languages. The idea is that any hardware layout, as specified by either a high-level language or an existing protocol, should be expressible in NetASM. Given a high-level protocol specification, the compiler can optimize layout in hardware using the assembler by composing or decomposing tables, reordering operations, or performing specific operations based on traffic profiles. The compiler might optimize for various metrics, such as power, area, or latency. NetASM also aims for target independence, or the ability to assemble the specified packet processing pipeline for different targets, such as those listed here. Let's overview a few key NetASM instructions. MKT, or make table, is an initialization instruction that takes two arguments, a dynamic table specification and a static table that has default initial values. BRTF, or branch, is a topology instruction that branches to the specified label if a header for a packet matches the contents of the table, and it sets the given header field with the matched index. Otherwise, it moves to the next instruction. Drop is a topology instruction that marks the packet for drop, and WRT, or write, is a control instruction that writes a table with a pattern at the specified index value. Let's quickly look at an example of NetASM in action with a stateful Mac learning application. The stateful Mac learner we'll look at has two tables, a match table and a modify. The match table matches on a destination MAC address and outputs the index or row of the table that successfully matched the packet. The modify table modifies the packet's output port depending on what index matched in the match table. There's also a register which simply keeps track of the size of the match and modify tables. Let's do a quick walkthrough of the stateful Mac learner. The first line sets a variable that defines the table size. The next 4 lines of code specify a match table with default values, and the following 4 lines after that specify the corresponding modify table. We then have 3 lines that are the initialization code for the Mac learner that make the match and modify tables, as well as a register with a default value of 0. The topology code at the bottom defines the control flow. The first line simply performs a test to see whether or not we have a match in the match table. If we do, we fall through to the next line, which loads the header with the appropriate modify, which modifies the output port of the packet, and jumps to the end. Otherwise, we have a miss. The next 2 lines populate the learning switch. The line after that floods the packet. Then we add 1 to the register value, indicating that the table has an additional entry. And finally, we test to see whether or not the register value has exceeded the table size, and if so, we set it back to 0. We can now run this code in an emulator. Emulator is going to generate 4 packets. The first 2 are from 1234 and 6543, respectively. Because the learning switch doesn't know any output ports for any destination, it will flood those packets, but it will also learn the output ports corresponding to 1234 and 6543, so that when packets H2 and H3 are sent, those packets are sent to the appropriate output port rather than flooded. We can see here in the run file that we've generated 4 packets and then generated an input sequence that sends those packets in order. The rest of the code simply instantiates the emulator and prints the output of the emulation. When we run the emulator, we can see, indeed, that the first 2 packets are flooded, but the next 2 packets are sent to the appropriate output ports. Other notable aspects of NetASM is that it's actually implemented under the hood in Haskell, so its semantics have provable verifiable properties. Each assembly instruction can also be associated with a cost to allow a compiler to make intelligent compilation decisions. In conclusion, programmable hardware allows the data plane to evolve, which in turn frees the SDN control plane from its current constraints. We've already looked at high-level languages that specify packet processing, and now we've looked at an assembler that could couple such a high-level language to low-level targets. The remaining missing piece now, of course, is a compiler. No such compiler exists yet, but perhaps the next time this course is offered, there'll be one.